All right, so now I want to think about a concept, and that concept's going to be the graph of the derivative. So let's start with a curve. There's a curve. So this will be f of x, and this will be x. And let's sketch a rough sketch. It's not going to be perfect. There's going to be things that we don't really know about. Let's sketch the derivative curve. So here, you'll notice that the slope of the tangent equals 0. So at this point, let's call it x1. Let's say that that's x1. The slope of the tangent is 0. So that point lies on the x-axis. Slope of the tangent here also equals 0. Let's call that x2. Now, let's look at some other things. As we go from here, we get a slope of the tangent that way. We get a slope of the tangent that way. We get a slope of the tangent that way. So what's happening is we're going from some pretty steep slopes, that. So we're going from steep to 0. And notice that all of these slopes are positive. Now, we know that slopes are positive when we get a rise over run, where we're rising from left to right. Okay, so this is rising left to right. And so we've got positive slope going from pretty high coming down to 0. And so that's kind of what that looks like. Going from pretty high coming down here. Let's look what's happening to the slopes as we turn in here. First of all, they're negative. You can't see, I'm sorry, my hand's in the way. So first of all of these slopes are negative. They're falling from left to right. So I should be down in this area. Notice that the steepest that they come is right there, right in the middle. This is the steepest slope that we're going to have. So that should be my lowest point. Okay? And then as I go from that steepest, lowest point, I start coming back around. Now notice that all these slopes are still negative, but they're increasing. They're going from really high negative to closer and closer to 0. That's actually increasing, guys, so it's actually looking something like this. Then from here, look at all the different slopes. We go from 0 to a positive slope, to a larger positive slope, to a larger positive slope, to a larger positive slope, right up like that. So, if we think about this for a minute, this is the graph of the derivative curve. This was our original curve. Let's pretend, now this isn't what this one is, but let's pretend that this curve was f of x equals x cubed. So the derivative would be given by the limit as h approaches 0 of x plus h cubed minus x cubed over h. Okay, so I got a bit of work to do. This is going to be x plus h, x squared plus 2xh plus h squared minus x cubed over h, limit as h approaches 0 of x cubed plus 2x squared h plus x h squared plus x squared h plus 2xh squared plus h cubed minus x cubed over h. That should go away with that. 2x squared h, and that's all I have of those, so it's going to be the limit as h approaches 0. Do any of the others go away? I don't think so. Can I put it? Oh, here, 2x squared h and x squared h, so I'm going to get 3x squared h's. xh squared and 2xh squared is 3xh squared, and then I have a x cubed over h. Trying to save some room here. As h approaches 0, the h is going to come out. 3x squared plus 3xh plus h squared over h. They're going to reduce because h does not equal 0. Turn the limit on. Ring-a-ding, ring-a-ding. it's going to go closer to 0. As this goes closer to 0, 3x times 0 goes closer to 0. 0 squared goes closer to 0. Our final answer is 3x squared. My point being, this is a parabola. This was a cubic. This is a cubic. The derivative is a parabola. Pretty interesting, and that's a concept.